All right, let's get right into it. We're standing at the edge of a huge transformation in how we design and run radio networks. I mean, forget everything you know about manual tuning and static planning. We're walking straight into the era of the AI native 6G radio access network. And that means a system that is truly cognitive and, well, autonomous. For decades, if you were an RF engineer, your whole world revolved around manual drive tests, wrestling with spreadsheets, and static planning. But that whole way of doing things, that human-in-the-loop, rule-based approach to optimizing a network, it's just not going to work anymore. To be blunt, it's broken. It has hit its absolute limit.
Because this is the new reality we're dealing with. Future 6G networks are expected to support up to 10 million devices per square kilometer. Think about that number. At that kind of density, and with the demand for sub-millisecond latency, trying to manually tune anything it's mathematically impossible. We've officially built something that's bigger than we can manage by hand.
So this isn't just a small step up from 5G. What we're facing is a full-blown complexity crisis for the entire industry. The scale, the density, the insane latency demands, all of it is forcing us to fundamentally rethink how a network even works, from the actual silicon all the way up to the services running on top. And that brings us to this really crucial shift in thinking. We're moving away from that old deterministic world, where an engineer follows a fixed playbook of rules. Instead, we're moving to a new, probabilistic one. The network is no longer this static grid that we configure. It's becoming a living, self-optimizing system that learns from its environment and adapts, all in real time. So how in the world do we build a cognitive network? Well, it all starts with a completely new set of tools. Let's take a look at the key technologies that actually make an AI-native 6G RAN possible in the first place. On screen here are what you can think of as the three foundational pillars of 6G architecture. We've got extremely large MIMO, or xMIMO. Then there's reconfigurable intelligent surfaces, or RIS. And finally, integrated sensing and communication, which we call ISAC. These are the brand new building blocks we get to play with. So let's zoom in on that first pillar, xMIMO. We're actually evolving from what we called massive MIMO in 5G to something now being called gigantic MIMO. We're talking systems with at least 256 antenna ports. This huge jump is absolutely critical for unlocking the new FR3 spectrum, the so-called golden band, which gives us that perfect sweet spot of bandwidth and coverage. And it's what enables fully digital beamforming. But all that amazing hardware needs a software revolution to go with it, right? And this slide shows that change perfectly. We are finally moving away from the traditional proprietary black box RAN, where a single vendor locks you into their ecosystem. We're moving to an open RAN architecture. It's open, it's programmable, and it's really the only way we can unlock all this new network intelligence. And inside that open RAN architecture, the intelligence is handled by something called the RAN Intelligent Controller, or the RIC. It's actually split into two parts. You've got the non-real-time RIC, which is like the strategic brain. It thinks long-term, using what are called RAPs. And then you have the near real-time RIC. Think of this as the reflex system, making split-second decisions with its own little apps, called XApps. Okay, so we've got the new hardware, we have the new open architecture. So now let's talk about how these pieces actually snap together to create what we're calling the cognitive leap, how the network literally gains a mind of its own. I absolutely love this quote from neuroscientist Dr. Lucy Lai because it's the perfect analogy for how an AI native network learns. Just like our own brains, the network learns to focus its resources on the things it sees most often. It gets incredibly good, incredibly efficient at optimizing for the situations that happen day in and day out. And here's what that learning loop actually looks like for an XApp running in the near RT RIC. It's this constant four-step cycle. First, it collects data from the network in real time. Then it uses that data to train its machine learning model. After that, it runs an inference to figure out the best thing to do. And finally, it sends a control message back to the network to make it happen. It's just observe, learn, act, over and over and over again. Okay, but this creates a huge new challenge for us, right? If the network has a mind of its own, and it's making all these decisions by itself, how do we know those decisions are any good? How do we know they're accurate or fair? How do we test its thinking? And that leads us to this really critical question. We hear all the time about AI models failing when they see something new. Can that happen in a network? The answer is absolutely.
If an AI can't generalize from the data it was trained on, it can create these massive hidden gaps in performance. And this slide gives you a perfect visual of what I'm talking about. This heat map shows the training data for a beamforming model. Look closely. You can see the data was only collected along that diagonal line. Now, the model might ace its tests on similar data, but it has literally no idea what to do in the corners. It's a classic failure of generalization because the training data wasn't representative. And if you don't catch that, it means terrible service for anyone in those corners. But let's assume we get this right. If we can build and train and properly test these cognitive networks, the result is a totally new kind of reality. The network stops being just a communication pipe. It becomes this sensing, sustainable platform. So this slide shows the concept of ISAC, integrated sensing and communication in action. It's pretty wild. The exact same radio signals that are connecting your phone can also be analyzed to detect objects in the world around them, like a car or a drone. So the network is doing two things at once. It's providing connectivity, and it's building a real-time map of its environment. And this cognitive power also makes the network more sustainable, because 6G is being designed from day one to be green. This number, 72%. That's the energy reduction they saw in a trial using ARM-based processors instead of traditional x86 chips for a 5G workload. The network's own intelligence will be constantly working to use the least amount of energy possible. So when you put this all together, the jump from 5G to 6G is just staggering. As you can see in this table, we're looking at an order of magnitude improvement in things like latency and device density, but the real change is that fundamental shift from just having some basic edge computing to a network that has AI baked into its very DNA. And all of this leaves us with one last big thought to chew on. We're building networks that are no longer just passive pipes for our data. They're becoming active cognitive systems that can sense the world and act on their own. So as we hand over more and more of this control, it forces us to ask a pretty profound question. How do we redefine trust between us and the intelligent infrastructure that's going to run our world?